Right, well, welcome to our second session of online training. Today we're going to be doing quite a few things. We'll start with just some engineering mathematics, because I'm afraid that we have to be able to do some mathematics. We're just going to do the mathematics that's relevant to you, just to try and get you up to speed. I know for some of you it's been a while since you've done maths. Most of what we're doing today is just to show you how to use your calculators. So, first thing I've got to do is I made a mistake last week, and I'm not sure what I said, but I think I got the inches and feet symbols the wrong way around. The symbol for an inch is a dick, and the symbol for a foot is a single dick. There are 12 inches in a foot. The inch is supposed to be a thumb joint. And a foot, of course, is supposed to be the length of a foot. Silly measurement system, really, but there you are. Kind of depends on the size of people's feet. Now, the first thing we're going to look at with mathematics is ratios and fractions. In fact, ratios is the old word for fractions, so they're the same thing. And as you can see from here, 2 over 3 actually means 2 divided by 3. Which makes easy sense. That can also be written 2 to 3. And the reason I say that is because if you think about 2 divided by 3, that actually equals, well, 2/3 really, about 0. What is 2 divided by 3 equal? I'll have to do it now. Oh, hang on. Anybody know what 2 divided by 3? Thank you very much.
Yes.
0.66. And this ratio here could be written 1. Oops, no, that's wrong. Don't do that, silly machine. This ratio here can be written 0.66 to 1. So, in fact, that... Oh, silly. This thing here, 0.66 recurring, is also what I ended up with here. 0.66 recurring. So, this is just a different way of writing a fraction. So, ratios, fractions, division, all the same thing. The type of ratio we're interested in instrumentation is what we call the turn-down ratio. This is the ratio of the highest usable, or what they call the highest effective capacity, so the highest usable value to the lowest usable value. If you take your average, well, tap, your average tap at home, it's got a turn-down ratio of about 10 to 1. Now what that means is if you can put maybe 100 litres a minute through your tap, the lowest controllable flow would be 10 litres a minute. Now obviously that's not the lowest flow you can put through the tap. The lowest flow you can put through the tap is nothing. But it's the lowest flow that you can control. If you try and go any lower than that, then it doesn't control very well. It either comes through all dribbly or it comes through all spurty. So that's the turn-down ratio, the ratio of the highest effective system capacity to the lowest effective system capacity. Not necessarily the highest flow to the lowest flow, the lowest controllable to the highest controllable. There are things called indices, which in fact are powers. I'm sure you're all familiar with the idea that 10 squared, is this one here, there, 10 squared equals 10 times 10, which equals 100. And 10 cubed is 10 times 10 times 10, which is 1000. Now, if you look at the number of zeros I've got here, I've got 3 zeros here, which is the same as the 3 I've got there. I've got 2 zeros there, which is the same as the 2 I've got there. And if you look at it, 10 to the power of 4, I end up with 4 zeros there. 10 to the power of 5, I end up with 5 zeros over here. So it kind of follows that 10 to the power of 1 would have 1 zero. And it turns out that anything to the power of 1 is just itself. And it also kind of follows that 10 to the power of 0 would have no zeros on. And it turns out that anything to the power of 0 is 1. And following the same pattern of dropping off zeros, when I go up the other way, the zeros start appearing on the other side. So 10 to the power of minus 1 is 1 over 10 to the power of 1, which is 0.1. 10 to the power of minus 2 is 1 over 10 to the 2, which is 0.01. Now, why this becomes important is because when we're talking about flows and speeds and accelerations, we often talk about meters per second. Now, by the laws of indices, that can be written, meters per second can be written meters second to the minus 1. So if you see something written on a page that say 20 meters second to the minus 1, what that means is that's the same as 20 meters per second, because they're the same, different ways of writing the same thing. Similarly, if you have an acceleration, meters per second squared, this thing, oh damn you, this thing, meters per second squared, then that can be written meters per second to the minus 2. So sometimes you'll see it written as meters per second squared, sometimes you'll see it written as meters per second to the minus 2. There is rules of indices, and the rules of indices are that if you have the same number and you multiply, then all you need to do is add the indices. So if you had 10 cubed, which is 1,000, and 10 squared, which is 100, you end up with 100,000. Now if you count the zeros, 10 cubed has 1, 2, 3 zeros, so that's 10 to the 3. 10 squared has 1, 2 zeros, so we've got 2 there, and 100,000 has 1, 2, 3, 4, 5 zeros, which is 10 to the 5. So you see 3 plus 2 gives me 5. So when you're multiplying numbers, you're allowed to just add the indices, providing it's the same number throughout. That's a general rule. And down here, so that you can look at in your own time, there's a little proof that that actually applies for everything. Because the only way that this equation can work, if you look at this equation, I've got c to the power of 0 times c to the power of b equals c to the power of b. What I'm going to do is I'm going to take the c over to the other side, and I end up with c to the power of 0 equals c to the power of b. It was multiplying on the left, so when I take it to the right, it has to divide c to the power of b. And c to the power of b divided by c to the power of b equals 1 every time. So anything to the power of 0 always equals 1. Fractional indices. This gets just a little bit complicated. If I write things out, if I have c to the power of a times c to the power of b equals c to the power of a plus b, or carrots to the power of apples times carrots to the power of bananas equals carrots to the power of apples plus bananas. If it turns out that apples and bananas are the same, say apples and bananas both cost the same, and if it turns out that 2 apples cost $1, no, I beg your pardon, 1 apple costs $1, therefore half an apple would cost 50 cents, what you could say is c to the power of half times c to the power of half equals c to the power of 1. Now that doesn't help at all unless I put some numbers in. I end up with an equation 9 to the power of half times 9 to the power of half equals 9 to the power of 1. And there's only one number where that will work, and that is if 9 to the power of a half equals 3. So that leads me to the conclusion that 9 to the power of half equals 3. When you say to the power of a half, that actually means the square root of. The reason I bring that up, in fact, going on from that, 9 to the power of the third is the cube root, 9 to the power of the fourth is the fourth root. The reason I mention that is because some calculators don't have a square root button on them. So with some calculators, if you need to find the square root of 9, what you have to do is you have to go 9, and then you use the button which looks like x to the power of y, and then you type in 0.5, and that will give you the square root of 9. Or sometimes that button looks like a top hat sign to give you the square root of 9. Right, so that's fractional indices, and the reason we need to know them is because some calculators don't have square root buttons anymore. Now, there's scientific and engineering notation. You can set your calculators up to give you either... yes, John, you have a question.
Yeah, I put in 3 square root 9 in my calculator and it comes out as 9.
I think you must have put in 3 squared. And that, because 3 squared is 9. So, square root sign, just in case you're wondering, you probably know, looks like that. Squared sign will probably look something like... And the other thing you may be aware of, or you may not be aware of, is you've probably got, on your calculator, I bet you've got a key which says that, and then another little thing which says that, which means you need to hit the shift key to get the square root. If you don't hit the shift key, you'll get squared instead. Does that help?
I'll sort it out. Cheers, mate. Thank you.
No worries. We can always go back after and have another little play with it. Okay, the next thing you'll need to do with your calculators is make sure that they're set to engineering notation. The difference is, in scientific notation, which they normally come set in, they always give out big numbers in something point a bunch of things. So, for instance, 937,865.3 in, that's this number here, in scientific notation it would be given as 9.378653. Everything is always given as something point a bunch, and then times 10 to the power of. Some calculators, instead of writing times 10 to the power of, write e to the 5. In both cases, what you have to remember is that tells you there's a 1, and then it gives you the number of zeros. So e to the 5, or 10 to the 5, there's a 1 with 1, 2, 3, 4, 5 zeros. And that's what we're multiplying it. So it's 9.37865 times that big number there, 100,000. In engineering notation, instead of going 9 point something or other, it goes to the nearest space. And we always space our numbers in threes. We always break them into threes using spaces. We never use commas. Now, those of you that weren't here last week, you may not know, but sometimes in European countries, in Germany for instance, and France, they would write 98,000 degrees C, and that would mean 98.000 degrees C. They use the comma as a decimal point. So we don't use the comma to separate our numbers. Not accountants use a comma to separate money. We don't use a comma to separate our numbers because we wouldn't be able to tell the difference between 98.000 degrees C and 98,000 degrees C. And if you're building the control system for a nuclear reactor, that makes a lot of difference. So with engineers, we space things with a space. And in engineering notation, we go to that nearest space. So 937,865.3 would be written 937.8653 times 10 to the 3, or in some calculators, E3. The reason we do that is because as engineers, we know that E to the 3 means kilo. So if you see 937.8653 times 10 to the 3, if that was meters, then that would equal 937.8 kilometers or kilometers, because E to the 3 or times 10 to the power of 3 means kilo. So engineers always go to the nearest third, because 10 to the 3 means kilo, 10 to the 6 means mega, 10 to the 9 is giga, and they go up in nice easy prefixes. So another example of scientific and engineering notation. If I had 0.004 of an amp, in scientific that would be written 4e to the minus 3, or 4 times 10 to the minus 3, depending on your calculator. In engineering, it would be written the same. Now, if I had 20 milliamps, in scientific that would be written 2 times 10 to the minus 2. But in engineering, it's still written 20 times 10 to the minus 3. And the minus 3 tells us we're dealing in millis. So because this one is written in minus 3, and this one is written in minus 3, what we would say is, oh right, here we have 4 milliamps and 20 milliamps. And they're both in the same order, they're in the order of milliamps. And here we have 65,000. Scientific would write it 6.5 times 10 to the 4. Engineering would write it 65 times 10 to the 3, because times 10 to the 3 is thousands, it's kilos. So if that was 65,000 watts, then that would be, in engineering, we could easily say, all right, that's 65 kilowatts. So engineering notation is a much more useful way of getting your results, because straight away we can see 10 to the 3 means kilo, 10 to the minus 3 means milli, and it's easy to get the sort of numbers we're used to dealing in.